Last time we derived an equation to integrate sine nth power x dx. We did that by using integrations by parts, and we obtained a reduction formula. The reduction formula that we obtained is given right here. We showed that I sub n is equal to negative 1 over n sine raised to the n minus first power x times cosine x plus n minus 1 over n times I sub n minus 2. So with each iteration of this formula, we can reduce the given nth power of the sine function to be integrated by 2. And we also discussed an example that was to integrate I7, that means integration of sine 7th power. And we completely solved that problem, and this was the answer that we obtained. This answer is somewhat long. There's no any other issue of this answer other than it being super long. Well, the length is okay because there are some mathematical questions where the answer is long. But on the other hand, there are some occasions where you will be in trouble, little bit of trouble, especially if your college algebra or trig are not so good. For example, let's say your professor wants you to differentiate all of these pieces and show that you actually have obtained the correct answer. That means you need to show once you differentiate all that, it becomes sine 7th power x. Well, in that case, there will be so many simplifications to be completed. Therefore, this reduction formula is not necessarily the best approach to integrate sine nth power x. Well, during the video today, I'm not going to discuss an alternative approach to integrate sine nth power x. In fact, it will be discussed as a future video. However, today I need to mention you something very important. About 350 years ago, a mathematician by the name John Wallis figured out something very interesting with this very same equation. That is, let's say you have to evaluate the integral sine nth power x dx not as an indefinite integral but as a definite integral. That means you will obviously have a certain lower limit and a certain upper limit, such as, let's say, from 0 to pi over 2. For such selected lower and upper limits, of course, which are important limits, such as 0 to pi over 2 or maybe 0 to pi, John Wallis observed that this first part of that formula, reduction formula, will be equal to 0. For example, if you pay attention to these two limits that I randomly chose, 0 and pi over 2, those two limits will make this first term of this reduction formula equal to 0. That is because if you put pi over 2 into this part, we know cosine pi over 2 is 0. Therefore, all of that term will be equal to 0 when the upper limit is substituted. Similarly, if you substitute 0, which is the lower limit of this definite integral, we know sine 0 is equal to 0. Therefore, all of this term will be equal to 0 for the lower limit as well. For both upper and lower limits, if this term is going to be equal to 0, then our reduction formula reduces to a finer formula as I sub n being equal to n minus 1 over n times I n sub minus 2. John Wallis, 350 years ago, used this equation to evaluate some important integrals between important limits such as 0 to pi over 2 and 0 to pi. So, we will see how to obtain that. So, today we will discuss Wallis's method. His method has two separate cases. One case is where this n is an odd number. The other case is where this n is an even number. So this video discusses only the case where n is an odd number. Alright, let's pay attention to the given integral and also the limits and thereby the new reduction formula. Alright, let's say I need to integrate from 0 to pi over 2 sine nth power x dx. Now, because of these nice limits, we know that our reduction formula has reduced to a finer form. I sub n is now equal to n minus 1 over n times I sub n minus 2. Alright, now we will see how to use this nicer reduction formula. Remember, we are going to discuss the case where n is odd for the discussion today. Tomorrow we will discuss the case where n is even. Alright, what's the smallest possible odd number for n? N can take 1. If n is equal to 1, well, in that case I'm not going to use this equation. That is because I will have this unnecessary I sub n minus 2 term on the right hand side, which will lead to sine negative first power x integration. Well, therefore I'm going to go ahead and evaluate n equals 1 case directly using the definition right here. Alright, so if n is equal to 1, we have I sub 1 being equal to 0 to pi over 2 integral sine first power x dx. We know integration of sine x is equal to negative cosine x, and then I have to substitute the limits 0 and pi over 2. And when you simplify that, we know we get positive 1 as the answer. So we need to remember that I sub 1 is equal to 1. Let's keep that in mind and move on to the next step. So in the next step, I'm going to use n equals the next odd number 3. If n is equal to 3, now I'm going to use this reduced reduction formula. When n is equal to 3, I sub 3 will be equal to, once again, look at this right hand side, n minus 1 over n. When n is 3, n minus 1 is a 2, n is 3, I, n minus 2 will be equal to 3 minus 2, which is a 1. So I sub 3 is equal to 2/3 I sub 1. 2/3 I sub 1 was found earlier as equal to 1. Therefore, I'm going to substitute 1 right here. Okay, so we evaluated I sub 3. Similarly, we will find the next odd number, which is n equals 5. When n equals 5, when I look at this reduction formula once again, I will have I sub 5, and on the right hand side, n minus 1 is a 4. In the bottom, n is equal to 5. I, n sub 2, n sub 2 is equal to 3. I sub 3 was calculated in the previous step, and that was equal to 2/3 times 1. I'm going to use those two results along with the 4/5 right here. Therefore, the answer can be written as 4/5 times 2/3 times 1. Alright, let's go on to the next odd number. So the next odd number is n equals 7. I sub 7 should be equal to, according to this equation, the right hand side, it will be n minus 1 over n. That means 7 minus 1 is a 6, and n is 7. I sub n minus 2, which is a 5. 6/7 times I sub 5. I sub 5 was found in the previous step as equal to all of that. So I'm going to use those 6/7 times 4/5. 2/3 times 1. At this point, the human mind can quite easily understand this sequence. But we will write it one more time. For n equals 9, it will be I sub 9 on the right hand side. Here's our equation again, n minus 1 over n times I sub n minus 2. Therefore, when n is equal to 9, it should be n minus 1 over n, which is 9 minus 1 equals 8 over n, which is 9. I, n minus 2, 9 minus 2 is equal to 7. And I sub 7 was proved to be equal to all of that in the previous step. So we're going to go ahead and use them. So this answer should be equal to 8/9 times 6/7 4/5 times 2/3 times 1. By this point, we can quite easily, for sure, identify the sequence. Look at this I sub 9 again. When I have I sub 9, in the bottom I have 9. On top I have 8. That means that same number 9 went to the bottom, 9 minus 1 went to the top. Alright, that's how that first part is identified. Now we can pay attention to the sequence in the bottom. 9 to 7 to 5 to 3. That means 9 minus 2 is equal to 7, 7 minus 2 is equal to 5, 5 minus 2 is equal to 3. On top also we can see the same thing. 8 minus 2 is equal to 6, 6 minus 2 is equal to 4, 4 minus 2 is equal to 2. And finally I have 1. Okay, now our minds can quite easily understand this sequence, and thereby we can write down the future terms. Say for example, I want to write the equation for n equals 11. It will be I sub 11. I can ignore all of these intermediate steps right here, and we can write down the answer directly. 11 will go to the denominator. On top it will be a 10. Now I have to keep subtracting 2 from each of the numerator term and also the denominator term. 10 minus 2 will be 8, 8 minus 2 will be 6, 6 minus 2 will be 4, 4 minus 2 will be 2. And in the denominator I will have 11 minus 2 equals 9, 9 minus 2 equals 7, 7 minus 2 equals 5, 5 minus 2 equals 3. The last term right here is equal to 1. Okay, now we will do an example. Let's say I need to evaluate the integral sine 15th power x dx between the limits from 0 to pi over 2. What should be the answer? Answer should be, in the bottom I have 15, on top I have 14, that's the starting term, and then we can write down the rest. I will write down the numerator terms first. 14 minus 2 is a 12, 12 minus 2 is a 10, 10 minus 2 is 8, 8 minus 2 is 6, 6 minus 2 is 4, 4 minus 2 is equal to 2. I will write the denominator terms next. 15 minus 2 is a 13, 13 minus 2 is 11, 11 minus 2 is 9, 9 minus 2 is 7, 7 minus 2 is 5, 5 minus 2 is 3, and all of that times 1. If you simplify this answer, you will see that this is equal to 2048 divided by 6435. Alright, that's how that equation can be efficiently used to evaluate the definite integrals where that first part of the term is going to be equal to 0. So please make sure to check that condition whether the first part of that reduction formula is going to be equal to 0 before applying these properties. Okay, let me repeat that advice one more time. Our reduction formula I sub n, when it was integration sine nth power x dx, the reduction formula I sub n was equal to negative 1 over n sine raised to the n minus first power x times cosine x plus n minus 1 over n times I sub n minus 2. Remember, when you have limits for the I sub n, some starting and ending limits, always check if this first term is going to be equal to 0 for each of those two limits, lower limit and the upper limit respectively. If that happens only, we can then write down that I sub n as n minus 1 over n times I sub n minus 2. Then we can repeatedly apply this theorem. And that one is actually very useful rather than evaluating the indefinite integral and substituting the limits at the end. That's because as this power grows, the final answer for the indefinite integral will be super long, and substituting each of those upper and lower limits will be tedious in that case. Well, there's a possibility that so many of those terms will be equal to zeros and ones as well. However, there will be so many things in between to be written down and to be simplified. Alright, I hope you enjoyed.